we're going to be doing a tutorial on how to do game prototyping with JavaFX. And JavaFX differs from the game development with things like Unity and Unreal and other engines because it's lightweight, and you do a lot of your stuff manually. So JavaFX has a lot of built-in tools for graphical utilities. It's mostly designed for like applets, Java applets. So there's a lot of user interface utilities. But in our case, we're going to basically make the framework of a simple game. And in this case, we're going to be making a basic version of Asteroids. So we're going to have a simple rudimentary physics system that we create manually. And a lot of the graphical stuff will be handled automatically. So the first thing that we're going to do with Eclipse open is we want to install JavaFX so that it's visible to the projects that we want to make. So we're going to go to Help and Install New Software. And here we're going to use a link which is going to differ depending on what version of Eclipse you have. In my case, I'm using Eclipse Photon. So the link is download.eclipse.org/releases/photon. It's going to be really similar for all of the different versions of Eclipse. And if you don't know what link this is going to be for you, you can just Google Eclipse software repository or something like that, and you'll find it pretty easily. With that here, you want to type e_fx Eclipse. Why is that not cooperating? All right, wait, let me grab this way. There we go. Okay, now it's working. I had to add it and then use it. So here with EFX Eclipse, we can see EFX IDE. We're going to select that and then go through the installation process, which I probably didn't need to do here because I already had it installed, but might as well. So while that's installing, we're going to, basically what we're going to do, depending on how much time we have, is we're going to construct a framework for the game that we're developing. And a couple times we're going to go through and add more features, and then we're going to see that it works, and then we're going to add a few more features, see that it works, add a few more features. And then we'll see how much we can get through in the time that we have. The JavaFX is sufficiently robust that in theory you could make a pretty advanced game. It actually does include 3D capabilities as well built in with cameras and perspective and things like that are pretty practical. Let me cancel this, but if you are installing it, make sure to go through and install the whole process. So with all of that done, now we can go to New Project, and here will be a category called JavaFX, and we can select JavaFX project. We can go to Next. I'm going to keep all the default settings, and I'm going to call it, obviously you can call it whatever you want. I'm calling it Asteroids 2 because I already have Asteroids 1, and I'm going to hit Finish. Now, I know that this is probably kind of small on the screen, but what it's going to give you is a couple things. It's giving you a project which has the JavaFX SDK, which in theory you could go through here and check out some of the things, and obviously the other JRE stuff. And then you have your source folder with an application. You have actually a CSS file that is currently empty that you can integrate with the main file that we're going to be working with, but in this case we're not going to be using CSS. It is pretty powerful though. So we're going to open up main.java. It comes with certain things pre-written here, but we're going to get rid of some of it. So yeah, as you can see here, there's application.css. We're not going to be working with that, but you absolutely could. So we're going to get rid of a couple things. You can keep override here, but I'm just getting rid of it because it's busy. And we're going to get rid of the contents of start. I'm going to change the name of primary stage to stage just because it's a little shorter. And now what we have is the absolute bare bones. We have the application type, and this is going to run our graphical interface. The main method is going to call launch. Launch, whatever function that is behind the scenes, is going to call this start function, and this is where we're going to do most of our work. Now, throughout this, we're going to be importing a lot of things. I'm not going to like go back and keep checking what the imports are up here as we automatically import a lot of stuff. So I'll try to keep that not too confusing. And we're going to take, so let's start taking advantage of a lot of stuff that Javafx has built in. The first thing that we're going to do is we're going to use the class point2d to, and we're going to say the size of the window that we want. And in this case, we're going to have the size of the window be constant, but in theory, you could have a variable size window, and the UI capabilities can have things react to window resizing and whatnot, but we're not going to do that here. So we have a point2d called size. It's going to be a new point2d. In my case, I'm going to say it's 1000 by 800, but there's no reason that you have to keep that the same. And let me just import point2d if it'll cooperate. Okay, and that's from javafx.geometry. Every now and then when you're importing something, it may the Javafx import may conflict with another import, such as AWT or swing. So make sure what you're importing is actually Javafx. Now we are going to we're going to start constructing the foundation of what we're working. So the first thing that we're going to do is we're going to use what's called a group. I'm going to use the prefix G for these, and it's called G root. This is going to be the root group, and we're just going to use a new group, and we're going to add children to this group to put things in the scene. All of the visuals are going to be object-based, right, instead of like rasterized or vectorized or whatever. So it's going to be really easy to display things. Now we're going to have our scene, which we're just going to call scene, and that's a new scene. The first parameter is the root node or group, and we're calling that G root. And then we're going to use size.getX. Well, that doesn't matter. Size.getX and size.getY. And that is going to make the actual window with a certain size. Now we're going to do stage.setScene. And so now it's going to be the main thing that actually displays in the window. Now just some other miscellaneous stuff. We're going to say stage.setTitle, and I'm just going to call it Asteroids, but that's arbitrary. And then we're going to say scene.setFill, and this is going to be the background color of the scene when there's nothing else on top. And there's a lot of different color utilities, and they're all based on the color class for JavaFX. But I'm just going to do, like you would see in CSS or whatever, there are certain default colors, so I'm just going to use color.black. But obviously, you can also make colors based on RGB values or things with transparency or HSB, and we're going to do some of these things later on. Okay, now if I do stage.show and I hit run, of course, it's opening on my other window, but we can see we have a blank black window called Asteroids, and nothing works yet. I mean, it works, but doesn't do anything yet, so it's not all that interesting. But we're going to have that all the way at the end after we construct everything. So first thing we're going to do is we want to see our frames per second, and we want to see how much time we've been in the game. So we're going to use what's called a label, and that is just a piece of text that displays. So we're going to call FPS label. And we're going to say a couple things. FPS label dot set translate x 2, so that's just moving the label over by 2 pixels. And then we're going to say FPS label dot set text fill and color dot white, so that we can actually see it. And all of these things, so group and label and a lot of the other stuff that we'll see later, all extend this really big class called node that JavaFX uses for like all of these different things. They all extend node, and they all have these different properties for translating and setting and adding transforms and whatever. So we'll see some of those later. Now to add this into the scene, we're going to grab G root and we're going to say get children, which is a list, and we're going to add FPS label. Now, the main thing that we're going to need, the most important thing that we're going to have in our game is the game loop. And for that, we're going to use an animation timer, which is another built-in thing, equals new animation timer. And we're actually going to make braces here and then close it. We're going to add import animation timer, and it's going to give me an error because I need to implement this handle method. This handle method is going to get invoked at the start of every frame. I'm going to rename this to nano because we'll see why that is in a second. Now, handle, we are going to, for now, just set the frames per second. So first, inside of here, we're actually going to set some variables. We're going to have the old time and the new time, which we're going to keep setting to see how much time there's been between frames. Right now, I'm going to set this as negative, and you'll see why in a second. Then we're going to have how much time has elapsed since the start of the game. Now, in here, we're going to say if old is negative, because it hasn't been sort of set up yet, we're going to say old is nano. Now, one of the most important things that we'll see throughout this entire process is this delta value. This delta value is going to be nano minus old over 1 times 10 to the 9. The time that we're receiving is in nanoseconds, and as you can see here, it is the time in nanoseconds, the current timestamp. So we're going to divide by 10 to the 9th to put it into seconds. So for 60 frames per second, this value is going to be around like 0.016%. Now we're going to set old to nano, and then we're going to add delta to the elapsed time. And then we're going to say FPS label, FPS label dot set text. And then I'm just going to use a string formatting for this. I'm going to say %.2f and %.2f so that we can have two floats that are truncated a couple digits. Here we're going to say 1 over delta, which is going to give us the frames per second that we're currently running at, and the elapsed time, which is going to show us how much time the game has been running for. Now, we're almost ready for the game to work. The last thing we need is loop.start. If we run this, I really wish it would not open in the other window the whole time. You may be able to see in the corner, we have time that's ticking up correctly in seconds, and then the other number is our frame rate around 60 frames per second. And in theory, if our frame rate dips, we'll still be counting time correctly, and that's important for a lot of different things, and that you'll see that in a lot of different game engines. Now, this is a great sort of starting point, right? So what we're going to basically do is we're going to add things in this area for setting up stuff in the game. And then after all of this boilerplate, we're going to have the stuff that occurs in the game loop. So let's see what we're going to add. Let's do input handling. So we're going to use the thing about input handling is that there are a couple different properties that we can use. So we're going to see when input is received on the keyboard by the scene. So I'm going to say scene dot set on key, and you can see there's key pressed, key released, and key typed. We want key pressed. And then new event handler, key event, friends, and then curly braces. And in here, we are going to implement another function called handle that's unrelated. So I'm going to import event handler. I'm going to import key event and make sure that it's not Java AWT, but it's Javafx. And now we need to implement handle. Now, the thing about handle is, let's try something out here. So key event, I'm just going to call this event. If I print out event dot get code, this will tell us what key it is. And if we look at the console, every time that I press, whoops, if I'm inside, I have to be clicked into the window. Every time that I press the W key while I'm focused on the window, or I press another key, right, it'll give me the key code. And there's, you know, various different things, right? The thing is that if I hold down a key, it will keep repeating, but like when you hold down a key in Microsoft Word or something, for a moment, it'll be slow and then it gets really fast, and we don't want that. We want it to be constant. So what we're gonna do is we're gonna remove this, and then we're gonna add a set, which is gonna keep track of what keys are down at any given time. So we're gonna say set key code, keys down, equals to hash set, and we will import java.util, java.util, and Javafx scene input. Now with that, we're going to add the key code whenever something's down. And then we want to remove it when that key's up. So I'm going to duplicate all of this. I'm going to replace pressed with released, and everything else is the same. And then I want to have this say remove instead. Now, if I go down to my game loop and I print out keys down every frame, and I run and I focus on the game, as I hold down keys, you'll see that it keeps track of everything that I have down while I have it down. And that is going to be perfect for us. So let's remove that for debugging. You can do more complicated things in these handlers, obviously, but for our purposes, it's very simple. So another thing that we're going to need, which is just going to make our lives easier, is we're going to have a function which sees if a key is held down. You'll see why it returns an int instead of a Boolean later on. And we're just going to say keys down dot contains k. If so, 1, if not 0. And that's just going to be a good shorthand for later on. So with all that set up, we're going to do a bunch of code now for actually setting up some interesting things for the game. So we need physics for this game, right? So what we're going to do is we're going to make a class that is a physics object. And we're going to make it abstract because we don't want to implement a physics object explicitly. We just want to inherit the physics object in child classes. So we're going to have physics object, and it's going to have various properties. We're going to have the position and the velocity. Now we're also using point 2D here as a 2D vector. The behavior is equivalent. We're going to have theta, which is the angle that the object is at, and omega, which is the angular velocity of the object. We're not going to be doing complicated physics. That's more for visual purposes. Then we're going to have the root of the object and a transform group. This may seem like overkill, but it'll make sense in a little while. And then we're going to see if the object is alive or if it is no longer operating. Then something that's going to come in handy for a lot of this is just defining tau, which isn't built into Java's math. So we're just going to multiply pi by 2 to give us tau. This 2 pi shows up all over the place here. And now we're going to make the constructor for physics object. We're going to get the parent group that we're going to add it to. We're going to get the initial position, the initial velocity, the initial angle, and the initial angular velocity. And we're going to say root is a new group, transform is a new group. We're going to add transform to root. And then we're going to add root to parent. Whoops, that should say transform. Now, we're going to say P is P naught, V is V naught. It's all straightforward enough. Theta is theta naught. Omega is omega naught, and we're starting out alive. Now there's a few more things that we're going to need. We want the update function, which we're going to call every frame. We want to know how many seconds have passed since the last frame, which is delta. We are going to add our current velocity multiplied by delta to our position. So you can think of our velocity v as pixels per second. When we multiply by delta, it changes it to pixels per frame. Now we're going to do the same with theta. We're going to say theta equals theta plus omega times delta, because that's degree or radians per second, mod tau. And modding it by tau will just keep it between 0 and 2 pi, which just keeps things nice. There's no like definite reason that that has to be done, but it just keeps things a little cleaner. Now, we're going to take advantage of all of these transformations that JavaFX has available. So we're going to take transform, which is a group. We're going to get its transforms, which may be a little confusing, and we're going to clear it. So far, there's nothing in them, but every frame we're going to add transforms as follows. Transform dot get transforms dot add all, so we can give a list of things. And we are going to add a translate, which is just a two-dimensional translation. So we're going to give the delta for x and the delta for y. And we'll import that. Now, notably, if you've done any linear algebra, because all this is implemented with linear algebra, the order of these matters significantly. So we're going to translate first, and then we're going to rotate by, annoyingly, this is implemented in degrees. So we're going to take theta, we're going to convert it to degrees. And now these two transformations will be applied in that order. Now we're going to want a destroy function, which kills a game object from the game. We're going to give it its own parent so that it can handle its own destruction, which may or may not be kind of gross depending on how you feel in sort of object-oriented style. And we're going to set alive to false. Now we're going to need an intersection function for collisions, right? The first thing we're going to do is we're going to make an abstract function that each physics object has to implement in its own way, called getShapeBounds, which is going to return a shape which we can intersect with other shapes. And this isn't incredibly efficient computationally, but it is clean. It is precise. So we're going to write public Boolean intersects, and we're going to take in another physics object from the one that we're currently in. The first thing that we want to check for intersection is that both are alive. And we're going to say shape.intersect, which is a static function. We're going to get this shape's bounds. We're going to get the other shape's bounds. Then we're going to say dot get bounds in local dot is empty. Bit of a pain, but it'll work. Notably, we have to say not here. So this is saying that the intersection between the boundaries of this object and the boundaries of another object is not nothing. So there is some intersection between the two shapes. Now we're just going to write two more static functions, which will come in handy every now and then. We're going to say static. Now forgive the fact that I'm using public in some places and public, not public in other places. I'm not incredibly concerned about the encapsulation from a OOP perspective. We're going to return a point to b called vec angle. we're going to take in an angle and a magnitude. This is just a way of constructing a vector based on an angle and a magnitude. We're going to return new point 2D. We're going to say math.cosine angle, math.sine angle, and then we're going to multiply by the magnitude. That's in some languages that's built in this case it's not. And then one more thing is we want to be able to get a random number in the range because we're making asteroids. There's going to be a lot of randomness that we need to include about where things are placed, their velocities, and so on. So we're going to say rand from the minimum to maximum, and we're going to return math.random times max minus min plus min. There are other ways to do randomness than math.random, like seeded randomness. In this case, I'm not worried about that. Okay, so we have this physics object, which has all these various properties built in, but it's abstract. We need ways to implement it. So there's a couple things that we need for asteroids. We're going to start with the ship. So we're going to say, and by the way, obviously this class and this other class that I'm going to make now, you can implement in multiple files, but I'm just putting it all in one file. We're going to say public or class ship extends physics object, and we're going to give it a thrust, which isn't really going to change, but I'm going to set that at 150 pixels per second. That's going to be its acceleration. And then we're going to use another type of node called a polygon to draw the ship. Now let's make the constructor. We want the parent and its initial position. We're going to call super for the super constructor for physics object. We're going to give it the parent, the position. Its initial velocity is going to be 0, which we can say 0.2d.0. Initial theta of 0, initial omega of 0, and there we go. Now let's set up this polygon, which we can just give as a list of points. So this list of points is going to be x, y, x, y, x, y, and so on. So I'm just going to, I already know that this will look like a nice little triangle. We're going to say start at x 0.7, y 0, y, or x negative 0.7, y negative 0.4, x negative 0.7, y positive 0.4. And this will make us a nice triangle. Now we're going to add to transform that group, get children dot add pgon. Now let's decorate this polygon. We're going to call set stroke, and I'm going to use RGB in this case, but you can make it any color you want. I just know that this color is going to be sort of a nice little pale blue. Then we can set the stroke width, which I'm going to set to 0.1, and you may think, well, that's not even going to be visible. Why would I do that? Well, you'll see right here, I'm going to add a new scaling of 30 by 30 to the polygon, and it's going to make everything bigger, including the stroke. And I just had these values be really small, right? And I had this be really small, and then I'm going to scale it up. It means I can change the size really easily. Then I'm going to call update. Actually, we'll get back to that in a second. I'm going to write a custom implementation of update. I'm going to override it. Update, I need delta. I'm going to get omega, and I'm going to get the throttle. Right? So based on the input, we're going to have some rotation, and we're going to have some thrust. If the throttle isn't 0, then I'm going to figure out what the acceleration is of the ship. And I'm going to get an angled vector at theta, which is the angle of the ship. And then I'm going to multiply thrust by throttle. And we're going to see throttle's just going to end up being 1 or negative 1, but usually just 1. And then we're going to say v equals v dot add acceleration dot multiply delta, right? So we're adding to the velocity with an acceleration, and then we're going to add to the position with that velocity. So, and you multiply by delta both times. If you've taken high school physics, then you know that you have delta t squared for the acceleration and then delta t for the velocity. If the throttle is 0, we want to slow down the ship a little because we don't want it to just go fast forever. So we're going to say v equals v dot multiply 1 minus 0.2 times delta. So that's just going to shave off exponentially a little bit of the velocity every frame, just to keep it from like going super fast. Now we're going to set omega to the omega input that we received, which is going to be a change in the ship's rotation based on input. And then we're going to call super.update with delta. And that will move the position. It'll update the transform and all those things that we don't want to rewrite it. The last thing that we need, which this is complaining about up here, is we need to implement the abstract function get shape bounds. And this is going to be really simple. We're just going to return Pgon. Pgon is a polygon, right? That's polygon. Polygon is a type of shape. So that's why we can return that due to implicit casting. And then a shape is a type of node. So that is done. Now, with all of that implemented, we can go back up to our game loop after these key things. A lot of these things that we're going to be doing, the order isn't really significant. It can kind of happen in any order as we construct things. Underneath here, I'm going to make a new group, G-game, which is going to contain all the game assets. We're going to make a new group. We're going to make a new ship, which is going to be inside of G-game. And then we're going to start it at half the width and half the height of the seat. I'm going to change this to G add all. I'm going to add G-game underneath FPS label. So in this order, FPS label is going to live on top of G-game, so we can always see the debug information on top of there. Okay, that was a lot. Let's see if it works. I have neglected to do something somewhere. Okay, yes. Go back here to ship, and I have to call update 0, 0, 0. That's just going to set up everything, but not move it, move the ship. When we call that, we get the ship right in the middle of the screen, but it doesn't move because we haven't handled the input yet. So we're going to go back to our game loop. Underneath this debug stuff, we're going to say rotation equals 4. This is just a constant that I found is nice. Key code.d. Obviously, you could use the arrow keys as well, but I'm using WASD. Key code.a. And that's there. So now we're going to see this is going to be 1 if key code, if D is pressed, this is going to be -1. If A is pressed, if they're both pressed, it'll cancel out, but otherwise we'll get a rotation. And we call ship.update with delta, followed by the rotation, which is omega, followed by whether W is pressed, which is going to be for thrust. Now, if we play the game, if I press A and D, they will rotate the ship. Depending on my rotation, if I press the thrust, it'll start to accelerate and then slowly decelerate and drift away, and I can fly around and have fun. And certainly that's plenty of fun on its own, but we need to make this game actually challenging. Next, we need to get some asteroids in there because it is called Asteroids. So we're going to make a new class, which is going to be another physics object. We're going to make it underneath ship, but obviously that doesn't really matter. I'm actually going to, I guess I can't quite minimize this in Eclipse. That's annoying. Class, class Asteroid extends physics object. And right now we're going to have it be a circle. If we have time, which I don't think we will, but if we have time, we can make it a little more interesting looking. But for now, these asteroids are going to be circles. We're going to give the parent the radius of the asteroid, its initial position, its initial velocity, and its rotational velocity, because the asteroids are kind of going to drift. Super parent P0, V0, 0, omega, because we're just going to start the angle at 0 because that's fine. As circles, we're not going to be able to see the rotation, but if we can add some variety to their shape, then we'll be able to see the rotation. We're going to say circle equals new circle with a radius, and we're going to set it to transparent so that you can see the outlines of the circles when they go over each other. Say circle.set stroke white. and we're going to set the width of the stroke to 3. Now, like we did with the ship, we'll say transform.getChildren.add circle, and then we're going to call update 0. And in this case, all the asteroid does is just float around. So we actually don't need to do a custom implementation of update. What we do need to do is implement get shape bounds, and we're just going to return this circle. Now, what is going to prove helpful is an asteroid construction function, because we need to, create the asteroids within the game. So I'm going to make a static function make. It's going to give us a parent, and it's going to give us the size of the screen because we want to start them off screen. What we're going to do is we're going to pick an angle relative to the center of the screen. We're going to say math.random times tau, or we can use that random range function, but that works too. We're going to set a radius of the asteroid somewhere between 20 and 30. Obviously, these variables you can tweak however you want. We're going to have the rotational velocity be between -2 and 2. Then what we're going to do, this is important, we're going to have the distance to the center of the screen be the magnitude, we're going to have it be the magnitude of the size of the screen, which is just the diagonal of the screen, half it, and then multiply by somewhere between 1 and 2. That means that the asteroid is going to start off screen somewhere between right off screen and like twice the distance off screen, meaning they'll show up at different times onto the screen. Now we can set up the location of the asteroid. It's going to be a vector at an angle with that is dis-center away. Then we're going to offset it by half of the screen size. Then we're going to make the velocity, which is going to be another vec angle. And we want it to be pointing back at the center of the screen. So we're going to take math.pi plus angle so that we rotate the velocity 180 degrees away back towards the center of the screen. And then we're going to add a little bit of randomness. So somewhere between -0.2 pi and positive, or -0.2 radians and positive 0.2 radians, so that they aren't just pointing exactly at the center of the screen. And then we want the velocity, we're going to have it be somewhere between 50 and 100 pixels. Now with all of this, we can return an asteroid with parent, radius, position, velocity, angular velocity. Whoops, that should be radius. Okay, so that is all done. Now we can go back to our construction of everything. We're going to make another group called G Asteroids, just so that we can layer everything a little better. And then we're going to add that to the game, to G game. And we're going to say ggame.getChildren.add G Asteroids. Now we need to keep track of our list of asteroids a little more practically than this. So we're going to have a separate list of asteroids. And it can be a linked list because we're only going to be iterating over it and adding and subtracting. So that there's just less overhead for adding and removing when it's a linked list. Okay, now that we have this, we want to say in here how many asteroids we want inside of the loop. So int asteroid count, we're going to start it at 15, which is again arbitrary. Now we want a for loop. So after before we get the ship input, we're going to say for asteroid aster in asteroids. We're going to update with delta, and that'll move them. Then we're going to say, well, asteroids.size is less than asteroid count. We're going to add asteroid.make. We're going to add it to G-asteroids, whoops, and with the size of the screen. So that means the very first frame, it's going to make 15 asteroids. And then as we destroy them in the game, it's going to repopulate the game with more asteroids. So now, if we play and we wait a moment, we'll see asteroids start showing up. Hello. Of course, there's no collision yet, there's no shooting yet, but they move around. So we still don't have a lot of actual behavior yet. Let's shoot some bullets. So we're going to make our final extension of physics object, and we're going to call it a bullet. It's going to extend physics object, and this one is also going to be really simple to implement. This is going to be a circle. We want a muzzle velocity, which I'm going to set to 400. And then we're going to construct group parent, the position, which is going to be the location of the ship, because that's where we're shooting from. We want the velocity of the ship to offset the velocity of the projectile, and then the angle of the ship. So we're going to call super on parent, the position. Then we're going to make an angle, which is the angle of the ship multiplied by the muzzle velocity, and then we're going to offset by the velocity of the ship. Then the rotation is going to be the angle, and omega is going to be 0. Yeah, so actually we're going to make muzzle static to be able to use it in super, and we're not going to be changing this anyway, so that's fine. We're going to instantiate circle as a new circle with a radius of 3. And I'm going to use RGB to make another color. This is going to be like a pale yellow. And then we're going to add it to its own transform. Why do I have this backwards? Oh, new. Okay. And then all we have left is, once again, shape, get shape, bounds, and we're going to return circle. But of course, this doesn't create any bullets. They don't exist yet. So we're going to go back to the top, to our construction area. We're going to make another group just for cleanliness, G bullets, new group. And we are going to change this to add all, so that we add the asteroids to the game. And then on top of that, we add the bullets to the game. Now, along with a list of the asteroids, we're going to need a list of bullets, which we can also make a linked list. Whoops, that should be bullet, and that should be linked list. So again, we're still not making them based on input yet. So we're going to go to here, into the game loop. We're going to want a cooldown for shooting bullets. So we're going to set that to about 1/3 of a second. And then the timer for keeping track of that cooldown is the bullet timer. Then after these asteroids update, we're going to do a similar thing for the bullets. So we're going to say bullet b bullets b.update delta. So that'll move the bullets. Now, alongside where we're doing this other input, we're going to say if key code dot space is 1. So if space is being pressed and the bullet timer has run out by being less than 0, we're going to set B to, we're going to make a new bullet, which is going to be inside of G bullets. We're going to get the ship's position, the ship's velocity, and the ship's angle. we're going to add this to the list of bullets, and then we're going to reset the bullet timer to bullet weight. And then we're always going to be decreasing the bullet timer by delta. Now we can shoot. So if I hold down space, it'll shoot at a regular rate. If I press it really fast, it still has to satisfy the cooldown. And there's no collision yet, but now we have these bullets that will shoot along with us. Now, another problem is that they don't disappear. Like, these all still exist in the universe, because once they leave the frame, they're still flying around, right? So let's handle that, right? Let's make sure that if something leaves the scene, it goes out of bounds, that it gets destroyed. So this is one strategy for doing it that I found last night, which is maybe not amazingly practical. We're going to use a rectangle, which is another type of node, another type of shape. We're going to make it the size of the screen like this. We're going to import it. We're going to make it invisible like this. And then we're going to add it to the root so that we can use it for collision. Well, fake collision, but okay. So we are going to make another function in the physics object class, which we won't have to re-implement in the other ones, which we're going to call leaving bounds. And this is going to tell us if something is out of bounds and is moving away from the bounds. Like, obviously the asteroids start out of bounds, but they're moving into the bounds. We don't want them to disappear. So we're going to say if shape dot intersect get shape bounds, and then the rectangle bounds dot get bounds local dot is empty, we return false, because we know it's not leaving. So if there's an intersection between the rectangle, which is the screen, and the shape, this physics object, then we know that it's not leaving the boundaries. Now we're just going to do some custom math based on the velocity, because if we're at this point in the function, we know that it's out of bounds, but we want to make sure it's moving away from the boundaries. So we're going to just use some shorthand, use some variables for condensing things. We're going to get x and y of the position. And then we're going to get bx, which is the bounds, the width of the bounds. And then by is the height of the bounds. And now we're going to return this complicated Boolean where if x is negative, so if it's on the left side and the thing is moving to the left, we return true. If it's on the right side and it's moving to the right, we want it to return true. If it's on the top and it's moving up, we want it to return true. If it's on the bottom and it's moving down, we want it to return true. There we go. So this will tell us if a shape is leaving the bounds. I don't know why it's highlighting like that. That's interesting. So if we go back here to our loop, we're going to do a couple of things. So the bullets, we're going to say if b.leaving bounds, then we want to destroy it from it and remove it from its parent. Otherwise, we want to update it. And we're going to do the same thing with asteroids. If aster.leaving bounds, then destroy it in G asteroids. Otherwise, update it. Now we want to remove things from the game that are no longer alive. They've been destroyed. So we're going to say we're going to grab that list of asteroids. It's already been removed from the scene, but we want to remove it from the game from the underlying logic. So we're going to say remove if a.a is not alive. It's just a nice little lambda function there. And then we're going to say the same thing for bullets. Bullets.remove if, so this is just a filter essentially, b is not alive. And then once that's removed, it means that asteroids will get added back in. The next thing that we want to do is handle collision between bullets and asteroids. So we're going to do a loop, and this is not especially efficient. We would probably want to use some smarter technique for this in another version, but we're going to iterate through the bullets. We're going to say if aster.intersect, which is that function that we wrote, bullet, then we want to destroy the asteroid and remove it from G asteroids. We also want to destroy the bullet and remove it from G bullets. And then we want to break out of this internal for loop. Now, if the asteroid's already dead, we don't want to worry about this part, so we're just going to skip it. And then we'll remove it later right here. With all of this, now, if we play the game, we can shoot the bullets, and as asteroids come in, if we hit them, they get destroyed. So there we go. Whoops, bye. But notably, we are still missing the player being able to die. So we're going to add a couple things there. We want some text to display when the player loses. So let's add that now to say like what their score was. So we're going to say, we're going to make another label. We'll call it lose label. And we're going to roughly move it to the middle of the screen. Again, there are better ways to do this, but this is janky. You can use like various sort of layout UI tools. We're going to move it roughly to the middle of the screen. And we will set the fill to white. It defaults to black, and that will not be visible. We're going to set the font to make it bigger, and we can just do font.font. And the size, so I'm going to set it to 30. This long. Okay. And then initially it's going to be invisible, so set visible false. So we now have this label, and we need to add it in. So we'll go to groot.getChildren, and we will put it above the game, but underneath the debug information, right there. Now, inside of the loop, we want to keep track of a couple more things. We want the score, which is 0, and that's going to be how many asteroids they destroyed. Then we want to know if they've died. In here, when a bullet has been destroyed, we'll increase the score by 1, or when an asteroid has been destroyed, rather. Now, inside of this loop, we're going to check if an asteroid has hit the player. So let's put that here. Sorry, we're actually going to put it here. So if the asteroid intersects the ship, we'll destroy the ship from game. We'll destroy the asteroid as well for good measure from G asteroids. And then we're going to take the lose label, set the text. We're going to use string formatting again. And we're going to say, you blew up. new line, you survived, float seconds, new line, and destroyed integer asteroids. Then our parameters will be the elapsed time and the score. Then we set the label to visible, set visible true, and we set died to true. Then we want to disable interaction if you've died. So all of this we're no longer going to do if you're dead. So we're going to first check if not dead, then we can do this interaction stuff and update the ship. So if we go in the game now, we can shoot the asteroids. We can destroy the asteroids. There's one, there's two, and I blew up. I survived however much time, and I destroyed 2 asteroids. The game keeps going, but I can't interact anymore, and my score is. Now we want to make sure, now one of the ways that you can implement asteroids is a looping screen. So if the ship goes off screen, it loops around to the other side. Instead, in this case, we're going to make it a little harder. We're going to say that if this ship goes out of bounds, that you also lose. So inside of here, we're going to say if the ship leaves the bounds, then we want to destroy it again. And this is inefficient, but I'm just going to grab all of this again. And instead of saying you blew up, I'm going to say you flew away. And everything else is the same. Otherwise, we want to do the other stuff with actually updating the ship and getting input. If we run that, now we can destroy asteroids. There's 1, there's 2, there's 3, and then we leave the screen and, oh, well, I hit an asteroid, that's inconvenient. If I destroy an asteroid and then leave the screen, I flew away. So that is now a fully functional version of asteroids. There's a couple things missing, right? The asteroids don't explode into smaller asteroids, but you could add the destroy function in here. You could override the destroy function and create more asteroids when something is destroyed. You can do that pretty easily. There's 2 more really quick things that I want to add. First is I want to add more asteroids out over time to make the game harder. So I'm going to add, along with the asteroid count, I'm going to add a timer. So asteroid weight equals 3. Asteroid timer equals 0. And we're going to do a similar thing that we did with that too. If we haven't died yet, then we're going to say asteroid timer equals delta. If the asteroid timer is greater than the asteroid weight, then we want to add another asteroid. Asteroid count plus, and asteroid timer equals 0. Start it over. So every 3 seconds, we'll get another asteroid. And this while loop will handle that. The next frame, it'll add an extra asteroid to account for the greater count. Now let's make the asteroids a little nicer looking, a little more various, taking advantage of polygons a little bit. This is a fun little technique. We're going to replace the circle with a polygon. And then let's get rid of all of that. And we're going to say pgon equals new polygon. We're going to set the stroke to HSB, we're going to use hue saturation balance. We're going to have somewhere between a hue of 20 and 50, which is between red and yellow. We're going to have a saturation somewhere between 0 and 0.2, so it's going to be very dull. And then somewhere between 0.8 and 1. So what this is going to do for the brightness, so this is going to be like a bright yellow, like a off-white, off-yellow, sort of brownish, light brown kind of variety. We set the stroke width to 3, and then we set the fill to transparent. And then we need to actually make the points, right? Because we didn't define any points. So I'm going to set 20, say there are 20 points. And what I'm going to do, I'm going to make a for loop to go through the points. I'm actually going to go around a circle and basically approximate a circle, but add some roughness to it. So we're going to have this angle is I times tau over points. So it's going to be somewhere between, you know, it's going to split a circle into 20 pieces. We're going to get the radius of this point from the center is going to be radius, and then we're going to have it be somewhere between 90% and 110% of that radius. And then we're going to get points instead of setting them. We're going to add the x value, which is going to be math.cosine A times r, and then the sine value is math.sine A times r. With that, we can say transform.getChildren.add begun. And here, instead of returning a circle, we return Pgon. Now we get these really pretty asteroids. It's only a little bit more effort, and we can actually see them rotating now. They have a little more variety. They're, I think, a little more menacing. And we can blow them the hell up. Oops. There we go. So that is a 1 hour, 350 line implementation of Asteroids with no engine, with no built-in physics, with no built-in much of anything. All that's really built in is the graphics. Obviously, there's a lot of things that you can add. I'll put the code to this up online somewhere, probably GitHub, and then I will also put a framework, which is basically like the skeleton of this, where it has the frames per second, it has the debug, it has the loop and all those kinds of things, so that you can make whatever game you want out of that structure. So there's also a lot of other things you can do. Like I said, Javafx has 3D, which is pretty powerful. You can do raster graphics, you can import images, you can import sounds and music. You can do entire user interfaces with buttons and sliders and all those kinds of things. There's a lot of power to it, and it's also just interesting to sort of build a game from the ground up where you have so little given to you except for the graphics that you have to make it yourself. It gives you a lot more control, but it's also more laborious. This particular strategy that I used for having an abstract physics object class and having this sort of layout with all the different groups that hold different things and adding things and removing things from those groups. There's a lot of different ways that you could set up the framework for a game like this. This is just the strategy that I found the most practical for this game. And I also, you know, Javafx benefits a lot from a lot of refactoring. You can completely refactor how a game is set up over and over and over again. As you can see, the frame rate dips on this every now and then. The biggest frame rate sort of problem for this is the computation of intersections, because the collisions are, when you determine intersections of these shapes, it actually computes what the shape is that they intersect at, not just a Boolean of whether they're intersecting each other or not. So that's a much more expensive computation. There are definitely more efficient ways to handle that, but Javafx doesn't have anything built in that's more efficient because it's not necessarily intended for that kind of like physics stuff. So there we go. That is Asteroids in an hour. Thank you for listening and hopefully following along. that's all I've got.